Good afternoon, everyone. My name is Mohammed Sahal Shaikh from the School of Science and Engineering at Curtin University, Dubai, and I will be presenting our project on sustainable passive thermal management for AI servers. Every time you use an AI model, every query, every image generated, every real time translation, a GPU server somewhere is operating at full power. These servers are really capable, but are also extremely hot. And the systems we have built to keep them cool are consuming nearly as much power as the servers themselves. This project proposes a fundamentally different approach, one that requires no energy at all. The thermal challenge facing modern AI infrastructure is one of the most pressing engineering problems of our time. GPU based AI accelerators now dissipate in excess of 700 watts per card, with a rack level power consumption surpassing 100 kilowatts in leading edge deployments. Globally, data centers consume approximately 200 to 250 terawatt hours of electricity annually. Of that, 30 to 50% is allocated not to computation, but to cooling infrastructure. The industry has responded to this challenge with increasingly sophisticated active cooling systems. The three methods most commonly used are air cooling, which is fundamentally constrained by the low volumetric heat capacity of air and becomes inadequate above approximately 50 square meters. Liquid cooling offers substantially greater performance but introduces infrastructure complexity, leak risk, and requires mandatory specialist maintenance. And lastly, immersion cooling, in which servers are submerged into dielectric fluid, represents the current performance frontier but remains prohibitively expensive to install, difficult to retrofit, and is problematic for long term component compatibility. The critical observation that motivates this research is that all three approaches share a single fundamental flaw. They are all active solutions, which means that each watt spent to cooling is a watt that does not contribute to a computation, and the servers they require continuous electrical input to operate. This study was designed around four specific research objectives. The first one was to analytically model one-dimensional thermal resistance of a Thassos marble aluminum composite casing to establish a performance baseline prior to simulation. The second was to conduct ANSYS finite element thermal simulations comparing all three materials, which is the pure aluminum, pure marble, and the marble aluminum composites, under identical boundary conditions. The third was to evaluate the transient thermal response of each configuration under a stepped workload profile, which represents current AI usage. And the last was to assess the sensitivity of peak operating temperature to marble panel thickness across 4 to 10 millimeters and identify the optimal design for a prototype in development in the future. Our proposed solution is a Thassos marble aluminum composite casing. As you can see on the left hand side, we have the Thassos marble outer panel, and then we have a flexible thermal epoxy interlayer and aluminum 6061 T6 skeleton, and this will make an entire composite casing. These combined properties make it intrinsically suited to passive thermal management. The composite architecture bonds outer marble panels to an internal aluminum alloy skeleton using a heat-resistant epoxy with a flexible compliant interlayer, which accommodates a differential thermal expansion between the two materials. The aluminum skeleton, with a thermal conductivity of 237 watts per meter Kelvin, provides rapid in-plane heat spreading. The marble layer provides a thermal mass, surface emissivity, and reflectance that enable passive dissipation. And along with that, we also have ventilated cutouts in the marble panels to allow natural convective airflow. Internal microchannels within the aluminum skeleton also provide the option for hybrid cooling integration in higher load configurations. And the result is a casing that is structurally equivalent to a standard aluminum chassis and is thermally superior for the specific workload pattern of AI inference deployment. The thermal analysis proceeded in two stages. The first was a one dimensional conductive thermal resistance model, which was applied to find a baseline performance. And through this, we can see the thermal resistance of the marble layer contributes to 0.022 degrees Celsius per watt, whilst the aluminum layer contributes to 0.00028 degrees Celsius per watt. The total composite resistance is approximately 0.0225 degrees Celsius per watt under a 400 watt steady state heat load. This yields a temperature rise of 8.9 degrees Celsius above ambient, which is comparable to a standard aluminum chassis with no active components whatsoever. For the finite element analysis, three-dimensional steady-state and transient thermal models were constructed in ANSYS Mechanical, the first one being pure aluminum, the second one being pure Thassos marble, and the last one being the marble aluminum composite. All the models are subjected to identical boundary conditions of 400 watts of internal heat generation distributed uniformly across the inner casing surface with an ambient temperature of 25 degrees Celsius. A mesh sensitivity study also confirmed that a 2 millimeter element size provided solution independence with less than 0.5% variation in peak temperature relative to a 1 millimeter mesh. As you can see from the results, the pure aluminum casing achieves a maximum temperature of 35.7 degrees and a minimum temperature of 35.4 degrees, which is less than zero point 0.3 degrees Celsius of a difference. The near isothermal behavior is a direct consequence of aluminum's exceptional thermal conductivity, which redistributes heat so rapidly the temperature gradients have no opportunity to develop. The Thassos marble casing exhibits a more pronounced temperature spread of 15.7 degrees Celsius, reflecting the marble's comparatively lower conductivity and its tendency to develop thermal gradient. Its average heat flux of 77.4 watts per square meter is 8.6% lower than aluminum, consistent with marble's high surface emissivity, enhancing radiative dissipation. The composite configuration in its current geometry shows that the lowest average surface heat flux of the three, 70 watts per square meter. This is 16% reduction relative to aluminum is attributed to the marble surface's elevated emissivity. The elevated peak temperature observed in the composite reflects thermal resistance at the material interface under the uniform heat distribution assumption of the model, which is addressed directly in the thickness study. The transient thermal simulation produced the most significant finding of this study. The marble thickness sensitivity study evaluated four panel configurations of 4, 6, 8, and 10 millimeters. Peak temperature increased monotonically, with thickness ranging from 48.6 degrees at 4 millimeters to 50.7 in 10 millimeters, and the relationship is essentially linear, with a gradient of zero point 0.3 degrees Celsius per millimeter. The minimum temperature and average heat flux across remains constant across all thicknesses, confirming that the aluminum structure governs the heat extraction rate, while marble thickness controls the localized peak. A panel thickness of 4 to 6 millimeters is identified as optimal, delivering peak temperatures below 50 degrees Celsius while retaining sufficient thermal mass for transient buffering. Based on these results, three different pathways are produced to reduce. For the first is to reduce marble thickness to the 4 to 6 millimeter optimal range. The second is incorporating phase change thermal interface materials at the marble aluminum bond to minimize interfacial resistance. And lastly, embedding aluminum pin-fin arrays on the inner marble surface to act as heat spreaders. This will then prevent the forming of heat hotspots within the material. The originality of this work rests on a genuinely unexplored intersection, the specific application of Thassos marble aluminum composite to AI survey thermal management has not previously appeared in the patent or academic literature. The significance extends beyond the laboratory. A server casing that passively buffers thermal bursts reduces the active cooling duty cycle, and each percentage point reduction translates directly to improved power usage effectiveness across the entire facility for edge AI development, remote inference stations, and smaller cluster installations where active cooling infrastructure is impractical or prohibitively expensive. The composite enables deployment scenarios that are currently inaccessible. The acoustic benefit of eliminating cooling fans enables AI server deployment in noise sensitive environments such as open offices and educational facilities, and the thermal inertia of the marble layer by reducing peak thermal stress on GPU component directly extends hardware service life, reducing both capital replacement costs and the embodied carbon of manufacturing new products. In conclusion, this is a solution that improves with simplicity, scales without infrastructure, and reduces environmental impact passively. In this study, we have already completed phase one, which is the analytical modeling and finite element simulation. We are currently in phase two, where we will deliver a physical prototype constructed from waterjet cutting. This will be done through waterjet cutting of Thassos marble panels and bonding it to a CNC machined aluminum skeleton. This prototype will be subjected to controlled GPU thermal loading across the 100 and 400 watt range with 500 thermal cycles durability testing and a comparative benchmark against a standard aluminum chassis. Once this is done, we will then deploy phase 3, which targets pilot deployment with an industry partner and scaling up to standard 1U and 2U server form factors, and a full techno-economic analysis benchmarking the composite against liquid cooling infrastructure. We are actively seeking funding, academic collaboration, and industry partnerships to advance from simulation to prototype, and this competition is a meaningful step in a journey. The data centers of the next decade will be defined by sustainability as much as performance. Tesla's marble aluminum composites represent a materials led answer to one of the field's most pressing challenges: passive, scalable, and requiring no energy, beyond that which the server itself generates. I thank you so much for your time, and I look